Now let's see some examples where we use the alternating series test. For the first example, let's take a look at the series sum from n equals 1 to infinity of minus 1 to the n times 1 over n. We already know that this series converges from before, but let's see if the alternating series test verifies this. So in this example, we have that Bn is equal to 1 over n. So let's check the two conditions in the alternating series test. For the first condition, we take the limit of the Bn's, and we want to get 0, and that is indeed the case for this example. The second condition is that the Bn's are decreasing. And again, this is true in our example, since dividing 1 by n plus 1 will give a smaller number than dividing 1 by n. Therefore, this series converges by the alternating series test. Now for a slightly more complicated example. Consider the sum from n equals 1 to infinity of minus 1 to the n times n over n squared plus 1. Here, we have that Bn is equal to n over n squared plus 1, so let's start checking the conditions of the alternating series test. First, we take the limit of the Bn's as n goes to infinity, and we get 0, since the degree of the polynomial in the denominator is greater than the degree of the polynomial in the numerator. So condition 1 is satisfied. Next, we need to check that the Bn's are decreasing. And this part's a little trickier than in the previous example. However, remember when we said that we could use derivatives to find when the Bn's are decreasing? Let's try and use that idea here. Let f of x be x over x squared plus 1. Notice that when we plug n into f of x, we get out our Bn's. Now, when we take a derivative using the quotient rule, we get out 1 minus x squared over x squared plus 1 all squared. To find when the Bn's are decreasing, we want to know when this derivative is negative. So let's set f prime of x less than or equal to 0 and solve for x. If we multiply both sides by x squared plus 1 squared, which is a positive number, we get that 1 minus x squared is less than or equal to 0. And then we can solve for x to find that x is greater than or equal to 1, or x is less than or equal to minus 1. In particular, f of x is decreasing for all x values greater than or equal to 1. This in turn implies that the Bn's are decreasing for n greater than or equal to 1, which is exactly what we wanted to show. Therefore, we verified the second condition of the alternating series test, and so we conclude that the series converges as well.